Hi everyone, this is David Stemper and welcome back to Using Forest to Teach About Math. This time around we're going to explore trigonometry. We're going to focus in on individual trees and measure tree height. We're going to be using a special little tool that foresters call the clinometer, a very handy tool, but we're also going to be exploring trigonometry. And for the teachers amongst you, you're going to be revisiting your trigonometry classes from your youth. And we're going to be exploring things like right triangles and what defines a right triangle. We're also going to be exploring trigonometric functions such as sine and cosine. You're going to be finding out why we use these aspects of trigonometry to help us determine tree height. But first, before we begin, let's review a little bit about tree growth and how trees grow. So I'll reiterate that when it comes to tree growth, we're going to be focusing on primary growth. That leader at the very top of the tree reaching up towards the sky as the tree grows taller year by year. In addition to the clinometer tool that we're going to be using, we're also going to be using a simple measuring tape, in this case a 100-foot measuring tape, to measure our distance, the distance between us and the target tree we're going to be working with. Okay, just a few more words about the clinometer itself. There are several different clinometers out there available through various vendors, but they all have some aspects in common. They have a window on the side that contains a level, and folks like archaeologists might use that level as they're working at ground level. If they unearth a certain artifact, be it a bone fragment or part of an ancient tool, they will record how that artifact was lying in the ground, and you can use the level for that purpose. For our purposes, the level or that window is important because it allows light in. And once you hold the clinometer, that light will come in through that side window and it will illuminate some important scales that are found inside the clinometer itself. And if you look inside the viewfinder, you'll find that there are two scales that share a common vertical axis. And on the right-hand side, you're going to have what's called the percent scale. We're going to be using that scale quite frequently to help us determine the height of the tree. On the left-hand side, you're going to see a degree scale. And that degree scale is going to help us to measure what are called angles of elevation and angles of depression. Again, that's going to become useful when we start measuring tree height on a slope. Okay, when we're using a clinometer to measure tree height, I want you to remember two important things I want you to measure. First, we're going to be measuring our distance from the tree itself. That horizontal distance, that straight line distance between you and the tree. That's relatively easy here on flat ground, that horizontal distance. We're going to measure that in feet. Secondly, we're going to need to use the clinometer to figure out what is called the percent reading from the clinometer. We're going to use the clinometer's percent scale to find the percent reading. Well, what does that mean? That means the portion of the percent scale that is taken up or occupied by our tree. Again, the portion of the percent scale that is occupied by our tree, top to bottom. So first, we're going to measure that horizontal distance from us, the recorders, to the tree itself, and we can use our measuring tape to do so. So using the measuring tape, the distance between us and the tree is 99 feet. Of course, we use the measuring tape, but if you're comfortable with pacing off the distance, you're welcome to do that as well. So what is a pace? A pace is two of your own steps. 1, 2. 1, 2. How many paces between you and the tree? You could pace off that distance as well. For me, I know that one of my paces is equal to 5.5 feet. So the distance between us and the tree, again, is 99 feet. You can use a handy measuring tape, or you can pace off the distance yourself if you choose. So we've collected the first piece of information, the distance between us and the tree. Second, we're going to figure out the percent reading from the percent scale on the clinometer. Okay, when you're looking through the clinometer, especially when you're doing it for the first time, it can be a little bit tricky. But the first thing you're going to do when looking through the viewfinder is you're going to find that horizontal black line. We call that the hash mark. Again, that horizontal black line, call that the hash mark, and we line up our 0 on the scale with that hash mark. That's what's called leveling off or leveling out, starting at the 0 point. So that's what we're doing. And if you look straight ahead, and line up the hash mark with the 0, you're looking straight ahead and you have an imaginary level straight line from you to the tree. And once you're confident that you're aiming at the tree and you have the clinometer leveled off at the 0 position, then you do what's called scaling up. Move the clinometer slowly until you see that horizontal black line, that hash mark, intersect with the very top of the tree, intersect with, in a conifer, what's called the leader. So what number on the percent scale intersects that black horizontal line? In our case, we have 110 or 110%. So we have those two important measurements. We have the percent reading from our clinometer, and we have our distance from ourselves to the tree. Distance of 99 feet from us to the tree, and a clinometer reading of 110%. So we multiply those two measurements together. Oh, but wait, we forgot one thing. Since we're working with a percent reading, we have to convert that percentage to its corresponding decimal. So divide by 100. So a reading of 110% would actually equal 1.10. We multiply 1.10 by 99 and we get 109 feet. So this tree that we've been measuring, this giant sequoia, is it 109 feet? Well, almost. We have to add one last thing to our measurement. If you recall, I asked you to point the clinometer straight ahead and level it out. If there was an imaginary line shooting off from the clinometer right now, what it would do is intersect the tree above ground. In fact, if I were standing right next to the tree, that imaginary line would be intersecting my head. So the last thing you do when you're measuring tree height on level ground is to add on the height of the recorder, the height of the measure, or in this case, my height. I'm 6'2", and that's 6.17 feet. And if you want to round to the nearest foot, which is what we'll do in these examples, you can add on 6 feet. So the height of this giant sequoia is 109 plus 6, or 115 feet tall. So is there another option besides adding on the recorder's height at the very end of the calculation? Well, there is another option. You don't have to add your own height. I mean, who's to say that we couldn't level out the clinometer and then scale down and see what percentage corresponds with the very bottom of the tree? You could do that as well. But recorder shake is a real issue. When you're first learning how to use a clinometer, the scale moves quite a bit as your hand shakes. So sometimes it's a bit annoying to try to capture that last percentage since your hand is shaking quite a bit. So because of that, I like to simply add on my own height at the very end of the calculation. So if we wanted to focus more on trigonometry as we wanted to determine the height of this tree, we could do so, again with the aid of our clinometer. I want you now to imagine a right triangle formed by the ground and the tree itself. Well, rather than imagine, why don't we just look at a drawing? Here's what I mean. So as you can see, two of the sides of the right triangle include the ground between us and the tree, that's one side, and then the tree itself is another side of this right triangle. And those two lines form what's called a right angle, 90 degrees. So we have a right triangle. So if you think about a right triangle and those old trigonometric functions, sine, cosine, tangent, etc., sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. Well, what is a hypotenuse? Well, it's that invisible line connecting me to the top of the tree itself. That's our hypotenuse. So we're going to use what's called the cosine function. Cosine of theta is equal to adjacent side over hypotenuse. Well, theta, what the heck is that? Well, that's a terminology we're going to use to represent the angle that we're going to be measuring. In our case, we're going to be measuring what's called an angle of elevation, using the clinometer to do so. So again, I'll ask you to look through the viewfinder of the clinometer, but this time we're going to be working on the left-hand scale, what's called the degree scale. Again, zero out your clinometer, that black horizontal line, line that up with the 0. Now you're going to be moving the clinometer up once again, but this time you're going to be reading the number that corresponds with the left-hand scale, the number that intersects that black horizontal line. That's going to be your degrees. And in this case, our angle of elevation is 48 degrees. So in terms of our right triangle, we're going to have cosine of 48 is equal to adjacent over hypotenuse. And the adjacent side is going to be that ground distance that we've already measured. So in our case, we're going to use the cosine function to find out the length of the hypotenuse. Again, the hypotenuse is that imaginary line connecting me to the top of the tree. We're going to use the cosine function. Remember, the cosine function from trigonometry is cosine of our angle of elevation is equal to our adjacent side over hypotenuse. Our adjacent side, again, is that horizontal distance we measured, 99 feet. So we have cosine of our angle of elevation is equal to 99 over hypotenuse. Let's isolate that hypotenuse on one side of the equation.
With the hypotenuse thus isolated, this is what we have. Hypotenuse is equal to the adjacent side, our horizontal distance, which is 99 feet, over cosine of 48 degrees. Referencing a cosine table, or simply a calculator if you have one handy, we find that cosine of 48 degrees is 0.6691. Plugging that in, we get hypotenuse is equal to 99 divided by 0.6691. Our answer is 147.9, which we will round to 148 feet. Finally, we can use the sine function from trigonometry to figure out our tree height. Recall that the sine function is equal to opposite over hypotenuse. In our case, that opposite side of the triangle is our tree, so we can call it tree height in this simple equation. We already know that our angle, theta, is 48 degrees, and we've just determined that our hypotenuse is 148 feet. So our equation becomes sine of 48 degrees is equal to tree height over 148 feet. Referencing a sine table, or once again a calculator if one is available, we find that sine of 48 degrees is 0.7431. Carrying out the basic algebra, we see that tree height is equal to 0.7431 multiplied by 148, which gives us 109.9 feet. We can round that to 110 feet. And finally, as in our first example, we'll once again add my height of 6 feet right at the end, since we are on level ground and the clinometer is recording its numbers 6 feet off the ground. This gives us our final tree height of 116 feet. So for all intents and purposes, we arrive at roughly the same tree height using the two methods. I recommend carrying out the latter method if you want the calculations to center on trigonometry to a greater degree. Regardless, you'll discover that trigonometry plays a significant role when determining tree height on a slope. This is what we'll explore next.
Determining the height of a tree on level ground is fairly easy, but things start to change a little bit once you insert a slope into the equation. So how do we determine the height of a tree that's found on a slope? In this case, how do we determine the height of a tree that's found upslope from us? Well, some things haven't changed. We still need two basic pieces of information. We need to determine our distance from the tree, again, the horizontal distance from us to the tree itself, and then our clinometer percent reading. Again, the portion of the clinometer percent scale occupied by our tree. So what's important to remember here is that as far as distance from us to the tree, we need the horizontal distance. that is not going to be the same as simply walking up to the tree itself and recording that distance, because that is not a horizontal distance. That's what's called a ground distance. It's going to be the hypotenuse of our right triangle. So this is where trigonometry comes back into play. I want you to imagine a right triangle superimposed over the landscape here. So in terms of that right triangle, I want you to imagine the tree that we're going to be determining the height of. Imagine the trunk of that tree extending down deep into the ground. That axis forms one side of our right triangle. The horizontal distance, that straight line distance between us and that axis of the tree, would require that we dig into the ground in order to actually measure that horizontal distance. We can't do that. So we can't measure that horizontal distance directly. But working with trigonometry, working with the cosine function, and measuring those things that we can measure is going to help us determine the height of the tree and determine that horizontal distance that we need. So, collecting two pieces of information first. That ground distance, walking up with our measuring tape to the tree itself and documenting that distance in feet, and then measuring the angle of elevation between us and the tree itself. So first we'll use the measuring tape to measure our distance from us to the tree itself. So using the measuring tape, I found that the distance between me and the tree was 127 feet. Now, you don't need to use the measuring tape. If you're comfortable with measuring distance via your own pacing, you can do that as well. My pacing is 5.5 feet for every one pace, for instance, and that would give me 127 feet as well. So again, we need to measure the horizontal distance between us and the tree, and the ground distance is part of that equation. We need to once again consider the right triangle and the fact that our ground distance between us and the tree is the same as the hypotenuse of that right triangle. The distance, the horizontal distance between us and the tree, again its trunk extended into the ground, that straight line distance, that horizontal distance, which is impossible to measure directly, we need cosine, the cosine function, in order to determine that distance. So consider the right triangle and the cosine function itself. In a right triangle, cosine of theta, our angle of elevation in this case, is going to be equal to adjacent side over hypotenuse. That adjacent side is going to be equal to our horizontal distance. That's what we need to determine. Cosine of theta equal to horizontal distance over hypotenuse, or ground distance. So we've measured that ground distance, we've measured that hypotenuse. So now we need to measure our angle of elevation. And that's where the clinometer comes in again. We're going to use the clinometer to measure that angle of elevation. Looking through the viewfinder, we're going to use the left-hand scale, which is the degree scale. So a few words about that angle of elevation. I want you to consider for a moment where that angle resides. It's actually formed by the lines of our hypotenuse and our horizontal distance. That again is going to go underground, looking straight ahead, if that trunk of that tree were to extend all the way into the soil. Where those two lines meet is actually down here at the ground. So one could argue, well, don't you need to get down on the ground to actually measure that angle? Well, no, we can keep things comfortable. We're still going to use the clinometer next to my eye standing up. So we need to account for that by actually focusing on a portion of the tree where your head would be if you were standing next to the tree. And to make things easy for me, I've placed an orange flag up on the tree where my head would actually reside if I were standing next to the tree. That way, as I'm pointing up at that target, I'm paralleling the ground. I'm paralleling that straight line formed by the ground if we were to walk up to the tree itself. So that allows you to remain comfortable as you take that reading. So again, looking through the viewfinder, we're going to use the left-hand scale. And if you're looking at the degree scale, first thing you do is zero out the scale itself. So you have that black horizontal line, line up the 0 with that line. And that's going to mean you're pointing right into the ground itself. So then you slowly move the clinometer up until that black horizontal line intersects with your target. And in my case, it's that little orange flag that I placed on the tree itself. If I were standing right up there at that tree, there would be an invisible line connecting my head to that flag. Read the degree scale at that point, and we find that we have an angle of elevation of 15 degrees. So in terms of our right triangle, in order to determine that horizontal distance, we need to use the cosine function. So cosine of our angle of elevation is equal to horizontal distance over hypotenuse, or ground distance. Horizontal distance over ground distance. We've determined that ground distance. That's 127 feet. Our angle of elevation is 15 degrees. So cosine of 15 degrees is equal to horizontal distance over ground distance. So in order to determine what our horizontal distance is, we'll be multiplying cosine of 15 by 127 feet. So cosine of 15 degrees, how do we figure out what that is? Well, that is another reason that the clinometer itself is a handy tool, because right on the side of the clinometer is a cosine table. It gives you cosine of certain angles, anywhere from 1 degree to 45 degrees. So you can use your clinometer on most slopes. Even if you don't have the angle that you want on your clinometer, there are cosine tables that you can look up on various math websites. So what we need is cosine of 15 degrees. So looking at my clinometer, cosine of 15 degrees is 0.9659. So we plug that into our equation. Cosine of 15 degrees equal to horizontal distance over ground distance. In order to find horizontal distance, we multiply 0.9659 by 127 feet. So working out that multiplication, 0.9659 times 127 feet is equal to 123 feet. So our horizontal distance, that distance between us and the trunk of that tree, if it were to extend all the way into the soil, is 123 feet. So to go back to the very beginning of this module, anytime you're measuring tree height, you need two vital pieces of information. And what are they? You need your horizontal distance, and you also need your percent reading from the percent scale of the clinometer, because the tree height is going to be a certain percentage of your horizontal distance from the tree. We've determined our horizontal distance, so now the last thing that we have to do is use the clinometer's percent scale to figure out what portion of that percent scale is occupied by our tree. So let's take our percent readings. Using the clinometer's percent scale, if I focus on the bottom of the tree, I have a percent reading of 23. Next thing I do is focus on the leader, the very top of that tree. The percent scale for the very top of the tree, the leader, is 65%. So what do I do with those two numbers? 65% and 23%. Well, I subtract them from one another. The portion of the percent scale occupied by my tree is 65 minus 23, or 42%. So our percent scale reading is 42%. In order to work with that number, we need to convert it to its corresponding decimal. So we divide by 100. So instead of 42%, we have 0.42. So we have all the information we need. The height of this tree is equal to our percent reading, 0.42, multiplied by our horizontal distance from the trunk of the tree itself, if it were to extend into the ground. Horizontal distance multiplied by your percent scale reading. So in that case, we have 123 feet multiplied by 42, 0.42, and that winds up being 51.6 feet. Round that to the nearest foot, 52 feet. So this tree is 52 feet high. So let's distill things a bit. This was a rather protracted way of describing how you determine tree height, especially for trees found on a slope. But what we did is very simple. We found out our distance from ourselves to the tree itself, walking up slope, measuring that ground distance. You're going to do that all of the time. You're going to capture your percent reading from your percent scale. That's the same regardless of where your tree is located. Level ground, on a slope, measure the distance between you and the tree, and take in your clinometer percent reading. However, when you're working on a slope, you also need to figure out your angle of elevation or angle of depression and take the cosine of that angle. So, put simply, the factor that you need to multiply by anytime you're on a slope is cosine of your angle of elevation or depression. That's what you need to factor in anytime you're working on a slope. So let's move in the opposite direction. How do we deal with things when the tree that you want to measure is located downslope? How do we determine height in that case? Well, the fundamentals haven't changed. We still need to determine our horizontal distance from the tree along with the portion of the tree occupying our clinometer's percent scale. We still need to collect those two pieces of information. Last time, when the tree was upslope, if we wanted to directly measure that horizontal distance, we would have needed to dig into the slope itself. Here, if we want to measure horizontal distance, we would need to magically float in the air. But I'm not David Blaine or any other magician, so I can't float in the air, so we can't measure that directly. But what we're going to do as well as last time is we're going to measure the ground distance, walking down slope to the tree itself, measuring that distance, and then measuring what's called our angle of depression. That's going to allow us to measure or determine that horizontal distance. So let's do that. Okay, well, we had to extend that measuring tape a couple of times, but what I found was that the distance between me and the tree was 220 feet. Again, we could have measured that via pacing as well. So in order to determine horizontal distance, we need to refer again to our right triangle. As you can see from that right triangle, we have our horizontal distance between us and the tree itself. So more or less, I'd be pointing up towards where the leader of that tree is. That's a straight line distance. That's one side of our right triangle. Just like as before, our ground distance that I just finished walking is our hypotenuse. That's the hypotenuse of our right triangle. So in order to determine the horizontal distance, I need to work once again with the cosine function. Cosine is equal to adjacent over hypotenuse. Cosine is going to be equal to our horizontal distance over our ground distance. I just measured our ground distance, 220 feet. I need to figure out what cosine of our angle of depression is. So let's measure that angle of depression. Just like before, in order to parallel the hypotenuse, I need to create a parallel line between the clinometer and the tree itself. So I placed some orange flagging tape where my head would reside if I were standing right next to the tree. Focusing on that and using my degree scale on my clinometer, I can see that the angle of depression is 11 degrees. So if our angle of depression is 11 degrees, what's cosine of 11 degrees? Well, we can refer to our clinometer again with the handy cosine table that's found on the side. Cosine of 11 degrees is equal to 0.9816. And from our cosine function, in order to determine our horizontal distance, I need to multiply my ground distance by 0.9816. So 0.9816 multiplied by 220, that's going to give us 215.9 or roughly 216 feet. Not a dramatic difference from our horizontal distance and our ground distance, but that difference becomes greater when you work with steeper slopes. So we've collected one vital piece of information. We have our horizontal distance. All we have to do now is get our percent reading. Again, the portion of this tree that occupies our clinometer's percent scale. So looking at the percent scale on our clinometer, if you zero things out, if you take that horizontal black line and line up the zeros, you're going to wind up collecting two percentage readings because you have to go down to the bottom of the tree and you have to go slightly up to reach the top of the tree or the leader. So I have two readings I'm collecting. The bottom of the tree corresponds with a reading of 20%. Going up in the opposite direction, we go to the other side of that percent scale and I get a reading of 2%. A lot of times when you're working with trees on a slope, especially when trees are downslope, you're going to be adding two percentages together because you have to go in two opposite directions on the percent scale. So in our case, we're simply going to add those two numbers together, 20 and 2, and that gives us 22%. So from our clinometer's percent scale, I obtain a reading of 22%. So we need to divide that by 100 to convert it to its corresponding decimal, so 0.22. So we need to multiply 0.22 by 216, which is our horizontal distance. Multiply those both together, 216 multiplied by 0.22 gives us 47.5 feet. If we wanted to round to the nearest foot, that would give us 48 feet. So this tree found downslope from us is roughly 48 feet high. Well, that's it for this module of using forest to teach about math. In exploring a little bit about tree height, we also explored trigonometry and we explored different aspects of the clinometer, a very handy tool. We've discovered that it doesn't matter where the tree is located, if it's on level ground, if it's located upslope, or if it's located downslope, there are still some basic fundamental measurements you need to take. You need to always measure the distance between you and the tree itself on the ground, measuring upslope or measuring downslope. That doesn't change. You also need to measure the clinometer's percent scale to determine how much of the tree you're measuring occupies that clinometer percent scale. So you're always going to be taking those two basic measurements, those two pieces of information. However, something else is added when you're working on a slope, upslope or downslope. It's at that point that you need to determine your angle of elevation or your angle of depression and take the cosine of either one of those angles. And that's going to be the factor you multiply things by at the very end when you're working on a slope. Working on level ground is easy. All you need to do is determine the distance between you and the tree, take your percent reading, multiply those two together, and you have it. So in all, it's a very, very easy method to determine tree height, and the clinometer is a very, very handy tool. So next time in using forest to teach about math, we're going to explore geometry. We're going to take another look at how you determine diameter and radius of a tree using some very basic tools, but we're also going to be setting up what's called a radial research plot. And the question is, how do you set up a radial research plot? How do you determine what size of a plot to use? That's going to give us a reason to explore geometry a bit more. But that's next time in using forest to teach about math. This is David Stemper, and we'll see you next time around.